Trickling in, feel free to fill out the survey that is linked via the QR code on screen. We'd love to see who's in attendance and reach out to you in the future. We promise your email will not get spammed. Hello all. Welcome to the undergraduate branch of the Center for Artificial Intelligence in Society's Spring 2020 Project Showcase, Showcais for short. My name is Ben Brooks, and I'll serve as this evening's host. As you can see, we are not running this year's showcase under normal circumstances. What would normally be an in-person on-campus event has been shifted online over Zoom. While I and the entire club would love to greet you all with handshakes and hugs, we're still incredibly grateful that you're able to take the time out to see what our teams have worked tirelessly to create. Before I hand it off to Lena, I'd like to take a moment to briefly introduce our club. Since its official inception in fall 2017, CAIS++ has worked tirelessly to combine artificial intelligence and social impact. When club members join, we take them through a semester-long curriculum. Not only is this curriculum undergraduate conceived and implemented, students learn theory and application simultaneously, with every resource open to the public on our website. From the conclusion of curriculum, members are encouraged to join small group projects. Given our focus on social impact work, many such projects exist as partnerships with research labs on campus and even some off campus. As of this semester, we've even broken up into the startup space. If you or someone you know has an interesting problem and an existing data set, feel free to shoot us an email at caisplus@usc.edu. We'd be happy to take a look. Furthermore, each semester features speaking engagements with industry leaders and academic researchers. This past year has featured a researcher at Google's self-driving car company, Waymo, a managing partner for a VC fund based in Venice, and a serial software company founder. Members get an opportunity to learn from and network with the best. For our introduction to tonight's project proceedings, I'll hand it off to Lena.
CAIS++ is driven to promote AI as a force for social good. And this mission can be seen in each of our projects. Over the past 3 years, more than 100 USC undergraduates in our teams have completed 32 projects that develop machine learning approaches that tackle meaningful, real-world, interdisciplinary societal problems. Our groups collaborate with professors, scientists, and industry engineers to work on projects with a range of applications, promoting medical, environmental, social, and cultural well-being. We're excited to have 5 of our groups from this semester present their work tonight. Each group has pre-recorded a presentation, which we'll be playing. After each presentation, we'll have a few minutes for each group to answer questions. Please type your questions in the chat, either during or after the presentation, and I will read them off to the group after the presentation is concluded. For the sake of time tonight, we likely won't be able to ask all of your questions, but we have contact information for each group on our Facebook event page. So feel free to reach out to the groups. After 3 presentations, there will be a 3-minute intermission.
And with that, we'll get started with our genomics project.
Hello, we are the CAIS++ Genomics Project, and this semester we worked on a generalizable method to classify genomic data. We worked with Andrew Smith and the USC Smith Computational Genomics Lab for this project. In their lab, they found that researchers frequently dealt with lost or missing metadata, or data uploaded to open access research databases entirely mislabeled, leading to frequent frustration. Traditional methods to figure out what's what at determining these metadata, which describe fundamental characteristics of the data, a manual and computationally expensive process, like read, mapping, or assembly, must generally be used. In addition, there's currently no generalized bioinformatics tool to find out a useful characteristic of their genomic data at the researcher's will directly from the data. The question is, can we use machine learning to recover these metadata characteristics directly from genomic signals quickly and efficiently? Our goal was to build a useful tool for any computational biology researcher to automatically determine characteristics of unseen genomic data. For example, is this set of gene reads from RNA sequencing or DNA? Are these gene reads from a human or from an elephant? Are these gene reads from healthy cells or sick cells? As I mentioned, doing so may require a reference genome. However, our method reduces the reliance on the costly building and mapping process so that the computational biology researchers can access crucial information about their data more easily, more readily, and more quickly. Our final product is to build a reference-free command line program, which we call GSEQ, GSEC, to automatically gather data from the sequence read archive for the type of model the user wants to build, and to try different machine learning algorithms so that the researcher can work with the best performing.
So for our data set, we used the publicly available data hosted on the NCBI Sequence Read Archive, or SRA. There, researchers around the world upload genetic data, which a lot of times contain wrong or misleading tags. These gene sequencing files come in a standardized format, which contains individual strings of length about 100, representing 100 nucleotides in series, as shown at the top of the slide. So we needed to find out a way of quickly extracting relevant information about the data to use as features. So the way we chose was to use k-mer counts as our only feature.
A k-mer is a subsequence of the genetic read of length k. The different lengths of k have different intuitive meanings. For example, k-mers of length 3 represent codons, and k-mers of length 6 could represent ordered pairs of amino acids. Considering k-mer frequencies as features allows us to build a model reference-free. The user can specify which maximum k value they want to pick, and the model building process is adjusted accordingly. The first step of the pipeline is querying the data from the SRA database and converting those files into the standardized FASTQ format. The data is streamed into a k-mer counting program for speed and usability with the help of Professor Andrew, so that each data point takes on the order of seconds to download. Once the k-mer frequencies have converged, the data is sent to model building, which trains several different models and saves the most successful one.
So this slide shows the usage for a program called GSEQ, which stands for Generalized Sequence Classifier. And it shows the intended usage and flow of the program. First, the user specifies which problem they would like to classify by entering special parameters. Then the program will look for trained models that match the information that was specified. And if a match isn't found, data will be automatically downloaded and pre-processed. Next, a data set is built and a variety of models are trained based on it. And then finally, the user gets a prediction report for the local data that they wish to classify. This scheme shows a usage example of the whole command line application, and it is divided into two subprograms. GSEQ train is used to train the classification models. As parameters, you can choose any pair of searchable fields in the SRA database and construct your model. That's why it's called generalizable. We can see two examples on the scheme. You can choose organism and then differentiate between strategies, or choose a sequencing strategy and differentiate between organisms. And then after the model is trained, the user can call GSEQ apply, which is a second subprogram. It will look for a trained model and classify the user's data.
Here we show the results of one of our test cases. Our GSEQ program automatically pulled whole genome sequencing data from our data source, the sequence read archive, for both human and elephant species. After the training process, it takes under 10 seconds to apply the model on the data. As mentioned earlier, the program attempts machine learning and statistical algorithms, namely logistic regression, naive Bayes, k-nearest neighbors algorithm, and random forests. We then pick the best performing classifier and save that model. At this point, the user can easily apply the model saved with the program GSEQ apply, directly from the command line to simply classify where the DNA came from. We found that logistic regression performs poorly, likely due to the fact that we have many more features than samples. However, naive Bayes, k-nearest neighbors, and random forests do really well in this binary classification problem. You can find our open source program GSEQ on GitHub. In terms of future work, we'd like to use a technique called lasso regularization to discover the most important k-mers found by the algorithms, giving additional resources to the researcher to ensure the validity of the classifier. We'd also like to move to multi-class classification and also develop a web app to automatically classify files posted on the web in a matter of seconds. Thank you so much for listening.
Thanks so much for sharing, Isaac. For now, we'll move on to questions.
I do think so, yes. Basically, we have a method that allows you to have like two different sources of data and differ between the two. So I don't have any really concrete example as to how it would specifically help with coronavirus, but in general, this is a tool that researchers can use to basically improve their workflow. And they're looking at the genetic sequencing of coronaviruses and all sorts of viruses every day. So hopefully it increases the efficiency and productivity of that process.
Yeah, our second question comes from Pranav. And how did you make sure that the data you used wasn't being overfitted?
We used, basically we tried the algorithm on a couple different machine learning methods, and we were choosing based on our, on data that it hasn't seen before. So we would train the model on a train set, and we had a basic train test split, and then we would look at the loss on the validation set, which is data that it hasn't seen before. In addition, we would sample randomly from the sequence read archive. So every data point would be like very new to the classifier. There would be a very low chance of overfitting because of that.
And the third question comes from Zane. He asked, has GSEC been used for anything else so far? And what was the lab you were working with using it for, if so?
No, we have just published this in the last week. So it's still like in its final stages of development as well. But we do believe that it's going to be extremely useful for especially the Smith Computational Genomics Lab. And since it's open source, basically any lab can use it as well.
Yeah, thanks, Isaac. Real quick, Pranav had a follow-up. Do you know what the size of the data set was?
Actually, that's up to the user's discretion. So as we alluded to, the user can basically specify the type of classifier that they want. So in the case in the previous slide was elephant versus human. And they can also specify exactly how much data they want to use. The more data they request, the longer it will take to download, but the more accurate the classifier will be. So that in particular case was 500 of each.
Cool. Thanks, Isaac. We'll shift to the next group.
Yeah, thank you.
Hi, everyone. We're one of the CAIS++ teams, and this semester we were working on creating agents to play Connect 4 by participating in the Kaggle ConnectX Challenge. So a little bit of background about our project. We wanted this to be an educational experience to us because we were all relatively new to reinforcement learning. And for those of you who don't know, reinforcement learning is basically a subfield of machine learning where you're trying to create an agent to act in an environment by maximizing a reward. So about our project, we were competing in the ongoing ConnectX competition. And although it's Connect 4 right now, in the future, they want it to be Connect anything. So it could be Connect 5, Connect 6, all the way up to arbitrary ConnectX. And to score your agent, they use an ELO rating system, which is the same system used to rank chess players around the world.
So the problem statement that we were basically given was given a board represented by an array, output the optimal move, which in our case corresponded to which column to place our piece in. And it turns out that Connect 4 actually can be solved, it's a solved game, it can be solved using Minimax, which is a recursive algorithm that chooses an optimal move for the player, assuming the opponent also plays optimal.
So there were a few challenges that we came up against in building our agents. The first one is that there's a very large state space for ConnectX. Given a 6x7 board with all the different permutations of where tokens can lie for each player, the number of state spaces is upper bounded by 10 to the 20th, like different board positions. So there's a lot that we have to consider when tuning our models. On top of that, you only have 5 seconds to make each move. So there's a limited amount of time for computations, and your algorithm has to be pretty efficient in order to make a move and not time out. And to that end, there are a lot of traditional algorithms like Minimax that are just impractical for this context because they take too long to compute. So we're going to go over some of the methods that we use now. I worked using a Monte Carlo simulation to play ConnectX. A Monte Carlo simulation basically relies on repeated random sampling from some initial point to find the best action or the most rewarding action. In Connect X, that looks like playing a bunch of random games and finding what the best move to start with is. So for any given board state, you can play in column 1 and then let 2 random players finish the game from there. And then you can do that for each column 1 through 7 and repeat that as many times as you have time for in that turn. And then at the end, you select the column that has had the highest reward or the best chance of winning. You go with that. So this is a pretty simple algorithm, but it's also very efficient.
So the model I pursued was deep Q networks, which are built off of Q tables. And Q tables essentially try to map every single state action pair to a Q value or a reward. And in this problem's case, the state space is simply the state action space is simply way too large and you can't explore it or store it efficiently. So deep Q networks try to approximate a Q table using neural networks. So the neural network I used pretty much had 5 hidden layers with sigmoid activation functions. And a neat trick I used in training this network was replay memory or an experience buffer, which aims to better understand or update the current model by gaining experience in one state and performing a batch update by randomly sampling from the replay memory / experience buffer. And this allows your updates to not be super correlated to this random sample, and also you don't have to update your model after every single run. So it greatly efficientizes the training of the network. And so the network performed very well against random, winning almost 90% of its games, but failed to understand how to exactly beat Minimax. Yeah.
I worked most of this project on trying to develop a genetic algorithm to play the game, where I was trying to evolve a neural network to learn how to play Connect 4. The architecture I used an embedding layer followed by 2 hidden layers, and then a final softmax output layer, which corresponded to which column to place the piece in. So I played against a variety of different opponents, trying a variety of different fitness functions. And ultimately, I was unable to generalize. So if the model was able to beat random or very simple players that would just place in one column repeatedly, it wouldn't actually generalize well on the latter. It performed relatively poorly when exposed to other players in the competition. So a little discussion about our results. The best result was the Monte Carlo method, which received a peak ELO of 1056, which was 40th in the competition out of the 347 teams that were participating. You can see the distribution of all submissions from all time and where we sort of lie on this histogram. We were the 87th percentile of all time submissions. So that's all for our project. We learned a lot about different reinforcement learning techniques, being all beginners to this space, but we're still looking to improve our model. We're thinking about adding an opening book for the Monte Carlo model, and also adding a fixed 2-step look ahead so that we can find positions more easily where the opponent may be forced into a loss or we may be forced into a loss in order to avoid those. So thank you all for hopping on this Zoom call and listening to what we had to say. We'd like to hear any questions you may have.
Before we start with questions, Zane, do you want to give an update as to the position of your algorithm?
Yeah, can everyone hear me?
Yes.
Okay. Yeah, so as of currently, we're actually ranked 33rd in the competition. So that's in the top 10% of submissions. And we're actually the highest rated publicly available code. So all the code above us is hidden and people don't want other people to see what strategies they're using, which is really cool.
Awesome. Thanks, Zane. We'll get started with the first question, which comes from Pranav. Have you looked at Minimax with alpha beta pruning?
Yeah, so the Minimax implementation was actually given to us by Kaggle, and it's an implementation called Negamax, which does have alpha beta pruning, but it also has further optimizations due to the fact that Connect 4 is a zero-sum game. So yeah, Minimax with alpha beta pruning still wouldn't be fast enough, and Negamax isn't even fast enough, even though it's even faster than that one. It's a good question, though.
See, I guess the other question Pranav asked was what was the winning method, but I guess you can't really see that, can you, if their code isn't public?
Yeah, all the code of the agents that are above us are hidden, but there's actually this kind of interesting thing that's been happening where a lot of the top performing agents are actually cheating and crash the game when they're about to lose, which is kind of funny, but we don't do that. So we might be rated even higher if they weren't cheating, which is kind of funny. They're looking to patch that soon, though.
Cool. And the last question is, have you tried any modifications on the basic Monte Carlo method?
Yeah, so we actually made two major modifications. The first one was if you're in a position where you can just win freely, you just make that move. You don't run the Monte Carlo simulations. And also, if you're about to lose, you just prevent that move. But then also, normally in Monte Carlo, you simulate the game by having random players play. But we actually replaced these random players with players that played almost always randomly, except there was if there was a winning move, they would play that move. And if there was a position where they had a forced move, they would play that. So by sort of modifying the algorithm to make it less random and a little bit more intelligent, we actually saw like a 20 place increase in the rankings.
Cool. Thank you very much, Zane. That was really interesting. We're going to move on to the next presentation.
Hi everyone. This year, my team and I partnered with Dr. Tremulet and the UC San Diego Kawasaki Disease Research Center to study whether or not machine learning and computer vision could be used to aid doctors in diagnosing Kawasaki disease. Kawasaki disease was first found in Japan in the 1960s. Since then, it has spread globally. By some accounts, it can even travel between continents via the jet stream. Today, it is one of the leading causes of heart disease in children and results in over 5,000 hospitalizations per year. What's cool though is that doctors already know how to treat it. The problem is just diagnosing it. Because the disease is so rare, many doctors have limited experience with its symptoms, especially since it looks like more common diseases, such as influenza. So our goal is to help with the problem of diagnosis. We really just want to prove that image-based diagnosis is a promising approach. Doing this would help convince regulators and patients to let us use more data to improve accuracy and create a legitimate medical tool. What's difficult about this is that for now, we can't use photos of patients. That means all of our data had to be collected from basic Google searches. We looked for images of Kawasaki disease and selected samples that corresponded to each of 4 different symptoms: red eyes, chapped lips, strawberry tongues, and rash. We did the same thing for lookalike diseases such as influenza. Then Dr. Tremulet graciously went through and labeled the data for us. Before passing that data into our model, we made sure to augment it using standard techniques like random cropping, rotating, color jittering, and flipping. This means that the model sees a few variations of every data sample, which helps it learn better. It helps ensure that our final model can generalize to unseen data as opposed to just memorizing the data set that we trained it on. Since our data set was relatively small, we wanted to be able to use transfer learning. This means that we take a model that's trained for a similar task and modify it slightly in order to help it understand Kawasaki disease. Specifically, we used ResNet 18 and DenseNet 121 architectures, both trained on ImageNet. We swapped out the model's final dense layers with our own dense layers. From a technical standpoint, these architectures are good at solving a variety of computer vision tasks because they make use of skip connections and bottleneck layers. That brings us to version 1 of our model. After training one model for each type of symptom, we got decent results. The table shows the quality of our predictions in terms of sensitivity and specificity. Sensitivity is the number of true positives divided by the number of total positives, and specificity is the number of true negatives divided by the total number of negatives. So basically, if we want to catch every case of the disease, we want sensitivity to be 100%. As you can see, our model performed pretty well when looking at lips, tongues, and skin, but it didn't do so well with eyes. The problem was that our data set was biased toward non-Kawasaki eyes. The model picked up on that bias, and so it rarely diagnoses Kawasaki disease. Obviously, this is a problem, so we set out to fix that with version 2 of our model. After weighting our backpropagation gradients according to the bias in the dataset, we drastically improved our results for eyes, taking the sensitivity number from 13% to nearly 97%. And so here you can see what our model sees in images of tongues. What's nice is that our model takes in small chunks of the image instead of the image as a whole. This allows us to tune the chunk size just as you might adjust the focus on a microscope. It also helps us visualize what the model is actually seeing when it makes a diagnosis. For example, we would want to make sure that it's actually looking at a strawberry tongue and not a plate of strawberries in the background of the image. This slide shows the same type of thing, but for lips instead of tongues. As you can see, the lips of the Kawasaki patient are much brighter than those of the other patient. The model is able to see the symptom. And so, in conclusion, we've determined that image-based analysis of patient photos is a promising means of diagnosing Kawasaki disease. More data would lead to even better models, and that's why we hope to continue working with this research lab in the future. Additionally, faster, lighter architectures like MobileNet v3 might allow this diagnostic tool to run in a smartphone's web browser, helping patients get the treatment they need in a more timely manner. Thank you.
Thanks so much, Hayden. We'll go to the first question from Roger, who asked, can you explain more about how changing the weight of the backprop gradients gave such impressive improvements on classifying from eyes?
Yeah, Matt, do you want to take this one? Okay, I don't know if he's unmuted. Basically, the data set for eyes was really heavily skewed in the negative direction. So we had a ton of samples of non-Kawasaki disease and very few samples that contain Kawasaki disease. And so the network just learned to say that everything was not Kawasaki disease. So by adjusting the loss function so that it favored the ones that are Kawasaki disease, that improved the results drastically.
Thanks. Our next question is, how quickly can your algorithm currently process an image, and what sort of speed up would be required to get it running on a doctor's phone, for example?
Yeah, so right now, it can process an individual chunk from an image, like one of those tiny little squares, in a fraction of a second. But since a whole image is made up of a bunch of those little squares, it can take up to like a minute to process a single image. And so we would want to cut that down by probably around an order of magnitude if we were to run it on something like a smartphone.
Cool. And we have a question from Pat. Was that validation or test accuracy that you reported?
So the accuracy was from the test set as well as the images that you saw. Those were from a test set. But the sensitivity and specificity numbers were for the data set as a whole, which is a little bit unfortunate. But it was just really hard. We didn't want to devote too much of the data set to test just because the data set was so small to begin with.
Thanks a lot, Hayden. We're going to shift into a 3-minute intermission before we begin our next presentation. We hope you all will stay on, just giving a short break. All right, we'll get back to it. From here, we'll start with density.
My name is Rador Dasgupta, and I'm the project lead for the density team. And this project is really exciting because it's actually CAIS's first collaboration with a startup, which is really, really cool. But it's also unique in that we're not actually focused on training a model. We're focused on another sub-process of the overall machine learning process, which is called data augmentation. But first of all, what is density and what is their goal? Well, on their website, they state it to be to accurately measure and monitor the density of people in your workplace without violating privacy. But I kind of like my three-word summarization a little better. It's essentially to count people anonymously. But why is this important? Well, of course, businesses want as much information as they can gather about both their customers and employees, because it can help them make better decisions about how to allocate their money. Just as a use case that they put on their website was to see how employees spend time in their kitchen. If they're spending more time towards certain equipment and less time towards others, then they can actually reallocate their funds to stop wasting money. But the important part is that customers and employees feel safe and comfortable. And this is the crux of what density is trying to do, is maintain privacy while providing this useful data. No one wants to feel like Big Brother is watching over their shoulders. Now, CAIS's part in all this is to help train their model by creating a pipeline to create synthetic data. So once again, the big picture, they're trying to count people anonymously, and they're going to do that using a sensor and a model. The sensor looking like the picture on the left, and the data that it's gathering like the GIF on the right, minus the rectangles and the numbers. But in order to train this model, it would be best if we could use simulations so that we could create an indefinite amount of simulations of different variety. So this is where we come in with our solution to use Unity to create a synthetic depth data pipeline of people walking through doors. And this breaks down to several sub-problems. So first of all, we need to find a human model which walks fluidly and a door that interacts naturally with this human model. Of course, we also need to gather depth data and be able to label it with ground truth. And the ground truth that density cares about in this case is which pixels are part of the human's head, the body, or simply just part of the background. So in order to get the human model, we looked in a couple of different places. First, Mixamo, which is a product of Adobe, and Blender. And we looked for human rigs. And all a human rig is just a 3D stick figure. And animators record the movement of the different ball joints in this rig to define different animations. So we ended up picking Mixamo because it was very easy to use, it was flexible, and it was free. Another indispensable tool for this project was the open source project, Unity ML Image Synthesis. Simply put, it's just a script that you attach to your camera object in the Unity scene, and it converts the virtual light that the camera is picking up and turns it into various types of data, including depth data, like you see in the top right, in which white represents being closer to the camera and black represents being further, and then object segmentation, which is what you see on the bottom, where basically different objects are labeled different colors. And this came in handy for the ground truth labeling aspect of our project. But first of all, let's show you the best that we could do with Unity to simulate walkers. So that's what you see on the left here. We have a pretty realistic rig with a skin, and it is interacting with a door in a rather natural way. Of course, it could be a little bit better. And in order to tackle the ground truth labeling problems, this is where we had to get a little creative with our solution. And as you can see, it looks kind of ridiculous, but there's this floating white sphere over the rig's head. And this is what we used to get around the problem of distinguishing the head from the rest of the body. Remember that the model doesn't actually care about what the camera is seeing, it only cares about the depth data. So this was a roundabout way of separating the head from the rest of the body, because if we put this sphere on a different layer, then the object segmentation step would be able to color it a different color and make it very, very easy to label the head. And so as we see, it actually come up with some pretty impressive results. On the right there, you see an object segmentation frame, and it is very, very clear that green is part of the head, blue is part of the body, and everything else colored in yellow is part of the background. So, in conclusion, we were able to use Unity and Mixamo to get a model of a human walking and use Unity physics to make it look like it's naturally interacting with a door. And thanks to the Unity ML image synthesis open source project, we were able to get depth data for it, all in service of the overall goal of data augmentation for the model of density's mission, which is to count people anonymously. And this is important because we want to avoid an Orwellian nightmare, keep customers and employees feeling safe and comfortable, while still providing businesses with valuable information for the company. Now I'll be taking questions.
Thanks. Our first question comes from Sarah. Do you know how density can count people anonymously without double counting individuals?
Yeah, good question, Sarah. So actually all that, just like the name of the company kind of suggests, all they care about is density. So all that is the number of people in a certain workplace and how that number changes over time. So like on their website, they'll show, they'll have one sensor just for their kitchen, right? And then all it cares about is the net number of individuals in that kitchen, and it's plotted over time to make sure that there are not too many. And so it actually doesn't matter about identification. All that matters is that from the depth data, it can see like someone passing under this line means that someone has just entered this zone. And the way that the sensor is set up is that if anyone enters the room, then they have to walk past that sensor, and same for if they exit. So they really just care about how many people enter and exit over time, basically.
Great, and I guess another question comes from Professor Zolkina. She asked, if they're keeping counts over time of people entering and exiting, how does the error accumulate over time?
Yeah, that's a good question as well. So we were talking with the density engineers, and they were telling us about the biggest problems with their model so far. And it's essentially small things like, let's say for some reason you had an umbrella. I don't know why you'd have an umbrella indoors, but that's an example they gave, or like some sort of object that's obstructing your head. Maybe you're holding your hand above your head, or you're wearing like a hoodie or something. These obstructions really hurt their model. And so the way that the error would accumulate is it would be basically random based on if the errors are occurring upon upon enter or exit. But because like, let's say that it fails to classify someone upon enter. If the same characteristic that led to that misclassification persists by the time they exit, then hopefully, it's a net zero. And then if that's not the case, then you hope that like the random distribution of enters and exits are roughly equal so that they cancel each other out. But yeah, in the end, this is the whole problem that we're trying to solve is lowering the misclassification rate.
Awesome. Final question. Pranav asks how more density equals less safety. If you give a brief explanation of that.
Yeah, so I'm not a spokesman for the name of the company by any means. I basically just got the mission from their website. I guess they call it density because they really want to see like one thing that they wanted to like give warnings about was if rooms were over capacity. So I guess they want to measure the density of humans in some part of the workplace, and if it's too dense, then they should be aware. Yeah, it's really less about safety, like physical safety, as privacy. I would say like privacy is really the main good that they're going for, because their whole selling point is that we're not setting up cameras in your rooms. We're just setting up these sensors that all they pick up is depth data. Adrian,
awesome. It's also worth,
good point about in this time, it could also be used for physical distancing. That's also a creative use.
Yeah, I also just wanted to add that it's pretty helpful. Like I talked to the engineers at Density and they're deploying it in lots of companies and warehouses as a security measure because it doesn't count exactly who's walking into which room, but it knows how many people are in each room. And that can help if like crimes are committed.
Cool. Thank you very much. We're gonna shift over to our last presentation.
Good evening, everyone. My name is Arman Pishori, and today my team and I will be presenting our project that we've worked on this semester, called the Deepfake Detection Project.
Hi, my name is Brittany Rollins.
Hi, I'm Zico Van Houten.
Hi, I'm Nisha Chatwani.
I'm Omar Uraimov.
So what are deepfake videos? Well, they're videos in which a person's face is synthetically replaced with someone else's. These videos are made using generative adversarial network, or GANs, which is another class of machine learning models. Deepfake videos have become a lot more prevalent than before with the advent of newer technologies. A recent common example is a video of President Trump giving his opinion on certain issues, when in reality, it's actually a video of an actor saying those things and then someone superimposed his face onto it. Such forms of media have a serious consequence in the spread of misinformation or fake news, and is why we decided to work on such a project. Here's an example of actor Jordan Peele in a comedy sketch on President Barack Obama.
We're entering an era in which our enemies can make it look like anyone is saying anything at any point in time, even if they would never.
Clearly, you can see the severity of these videos through the accuracy at which it nails President Obama's face. Our goal for this project was to build a deepfake classification model to combat the spread of fake news. My thought process in starting this project was to divide the group into two halves, each focusing on two major parts of building a machine learning model. One handled pre-processing the data given, and another handled model building. When it came to model building, we started by building a basic model, and after observing the results, we explored different avenues, of which we compared the results to the initial model.
This semester, our group participated in Kaggle's deepfake competition contest. The dataset given to us by Kaggle consisted of 500 gigabytes of videos, and these videos were diverse and unbiased, meaning that the people in them consisted of a wide age range and a range of ethnicities. The videos also varied in video quality and brightness levels. And just to show you what our data looks like, here are two screenshots from videos given to us. The one on the left is real and the one on the right is fake. Initially, in pre-processing, we wanted to work with Coco's dataset, but we later decided to move to OpenCV because it was much faster in processing videos. And in this process, we use OpenCV to identify the facial region, and then we manually blacked out the rest of the video.
So as for our models, we wanted to begin with a basic RNN and CNN model architecture of no pre-processing, and then investigate two methods being the eye blink detection and color histogram methods. For our basic model architecture, we wanted to build an RNN which would look at a sequence of data in time on top of a CNN, which would look at image data. However, we needed to find a way to input the video data, and so we used a video frame generator to split up the video file into a sequence of frames that would then be fed into the base model.
Our next model focuses on using eye blink detection. There are very few images online of faces with the eyes closed, and without training images of people blinking, deepfake algorithms are less likely to create faces that blink normally. Therefore, characters in deepfakes blink a lot less frequently in comparison to real people. We used OpenCV to detect facial landmarks and count the number of eye blinks, as you can see in the counter in the top corner of the video. Then we passed in that data to a KNN classifier to predict if a video was a deepfake or not.
Our next model is based off of research conducted 2 years ago that found that it is possible to differentiate real and fake GAN images solely based off of their grayscale histories. The grayscale histogram measures the distribution of how exposed and underexposed an image is. So basically all images have a certain exposure based off of the camera it was taken on, and GANs experienced some difficulties when trying to recreate this exposure level. The researchers also tried using color histograms. However, this method proved ineffective as GANs are more accurate at mimicking colors than they are at mimicking exposures. In our next slide, you'll see how we attempted to extend the findings that the researchers made on image classification to video classification so that we could use it as the deepfake detector. I extracted the grayscale graph out of every frame and then ran it through an RNN.
So in the end, the base model had an 82% accuracy of no preprocessing.
The iBlink model had an accuracy of 82% as well.
The grayscale model is currently being trained, and we'll update you about the results during the question phase.
To further the work we've done, we've taken a couple steps. Right now we have a website running where one of our models is housed to give people access to our technology. And hopefully with the website, we will be able to combat some of the misinformation that's spread. We are also writing a research paper to talk about our methods and what worked and what didn't work as well. We would also like to implement other models, specifically using face edge detection. And we'd like to run our models on much larger data sets because we were only able to use a small portion of the data given to us. And lastly, just to bring everything together, we think what our work is so important because, as I said earlier, there's a lot of misinformation online and fake news, and especially with phenomena like the coronavirus, we need to combat that so people aren't doing the wrong things or doing anything harmful. Thank you, and now we'll take questions.
The first question comes from Shamik. He asks what was the recall specifically on deepfakes as opposed to the overall accuracy?
Yeah, so what we meant by accuracy, my bad, was that it was actually the recall. The overall accuracy actually aimed to be a little bit higher than that. So yeah.
And the next question comes from Zane, who asked, is there any way to prevent these kinds of models from being used themselves to create better deepfakes?
Yeah, so for the most part, we try to extract certain features that are limited in the technologies currently used to produce deepfake videos. However, such as our color histogram model, it's very tough for people to actually build deepfake videos without actually creating without actually affecting the color histogram of the video. So that method actually seems to be one of the more prominent and more interesting ones, since it's hard for other people to actually use that information to combat or to build better deepfake videos.
Yeah, a couple more questions here. Professor Dilkina asks, can you combine the two features, eye blinks and color, to fit a joint model?
Yeah, so currently our research in this topic hasn't ended yet. We're still currently pursuing it, and we plan to pursue it over the summer. So yeah, that is one a really interesting idea to pursue in the future. But yeah, additionally, I'd just like to update you guys on the accuracy of the grayscale histogram that we ran. So running it on a small data due to complications with getting access to the entire data set, we were able to achieve a 77% accuracy, or sorry, recall. And over time, and the next time we're going to run this model, we're planning on adding a CNN and training it on the entire data set, which is about 60,000 videos. And approximately these models take over a night to run. So hopefully once we do that, we'll be able to collect our findings, and it'll probably improve the model.
Awesome. Thank you guys very much. And with that, we've completed our set of project presentations for the semester. It goes to show what good can be done if you guys all put in the work. And before we completely wrap up, I'd like to take a moment to thank all those who make our work possible, especially our faculty advisor, Dr. Bista Delkina, who has supported us in her work as our parent institution's faculty director. And as a side note, let's give her a virtual round of applause for recently earning tenure at USC. We're super proud of you, and we're extremely grateful for all that CAIS does for our undergraduate. I'd also like to extend a brief thank you to the 2019-2020 e-board. Just to list off everyone's names: Grant Stenger is Vice President, Lena Mather is our Projects VP, Raj Dua is Projects VP, Zane Durante is Curriculum, Shannon Brownlee is Fellowship, and Sean Syed is Operations. Also an honorable mention to Sam Tripp for leading Fellowship last semester. I'd really like to thank you all for attending our event this evening. It's really refreshing to see all the supporters of AI for social good. If you have any follow-up questions, feel free to check out our Facebook event, shoot us an email at caisplus@usc.edu, or check out our website at caisplus.usc.edu, both of which will be posted in the chat. Thank you again. It's been super fun to host this event, even though it was on Zoom.